let's talk about pacemaker cells. I'm going to actually draw out the action potential for a pacemaker cell. And remember, this is time over here. And let's do it with millivolts. This is positive up here and negative down here. Now, our pacemaker cells, let's specifically talk about the ones in the SA node. So these are SA node action potential, and you know it starts out kind of negative and creeps up. And that's mainly because of sodium leaking into this cell. And other ions are present as well, but that's the major ion. Now it gets up to this point, right, where I'm drawing kind of a threshold. And this threshold is for what? Well, this is kind of this dashed line kind of represents the point at which calcium channels start to open up. And so they open up and causes the cell to become even more positive. So it was already going positive. It's going to go even more positive, and it's going to get to about that point. And then finally, at this point, those calcium channels, those voltage-gated calcium channels close down, and potassium channels open up, which causes the membrane to repolarize. So these are the kind of three phases we've talked about, right? This is phase 4. We numbered it as phase 4. This is phase 0, and this is phase 1. These are the three phases we discussed. So now let's think about it a little bit harder. Let's say that we view this, and I think that's a pretty reasonable thing to do, view this as the heartbeat. This is one heartbeat, right? And you know, if we were to kind of keep this picture going, basically you get another one of these and another one of these, and it would just basically continue. And this is what our heart rate then looks like, right? If you were just to look at a strip over, let's say, 2-3 minutes, it would basically be just one after another of these kinds of action potentials kind of stacked on each other. So now if I was to take this heartbeat and shorten it, let's say I was to make it, instead of ending where it does, let's say I ended it right there, so that this whole thing kind of gets brought this way. Well, it would crunch down my action potential in phase 4. But what would that mean exactly? I mean, you might think, well, so what? So it's a little bit more crunch down, happens a little faster, so what? Well, what it means, if you think about it, is if the heartbeats are stacking on top of each other, if you make the heartbeat itself a little bit quicker, meaning takes less time to finish, then the next one can start a little bit early, and then that one will finish early, and the next one will start early. And basically at the end of a minute, you'll have more heartbeats kind of fit in. So by having a shorter heartbeat, what you're really saying is that you're increasing the heart rate. The number of heartbeats in a minute goes up. So that's actually pretty powerful, because we think about heart rates all the time, but rarely do we think about exactly what that means for each individual heartbeat. And what it means is that each heartbeat goes quicker. Now, the opposite is true too, right? You can imagine actually extending this out. Let's say the heartbeat actually goes a little bit longer. You could extend it out that way. And if the heartbeat goes longer, then that means that you can get fewer packed into 1 minute. And that means that you're basically saying that you're reducing the heart rate. So when I say I'm increasing or decreasing the heart rate, really what I'm trying to say is that I'm shortening or lengthening the heartbeat. So that's actually, I think, a pretty powerful idea. Now let's take it a step further. Let's actually do a little thought experiment. Let's imagine that this is 1/10 of a second right here, 1/10 of a second. And it may not be exactly 1/10 of a second, but let's just imagine it is. And let's say I wanted to take a look at our cell at this point, because that's where 1/10 of a second has hit. What would our cell look like? Let me actually just make a little bit of space on our canvas and draw out what our cell might look like at 1/10 of a second. And just to make sure I keep everyone kind of on the same page, this is what's happening in our cell, our pacemaker cell, at 1/10 of a second. So at this point, you have a cell. Let me actually draw a blown up version of our cell that might look like this. And this cell is going to have ions flowing in. It's going to have, let's say, sodium coming in. And we know that this is the dominant ion. So let me draw, let's say, a few of them kind of gushing into our cell. And we also have some other ions coming in. And you might think, well, wait a second, I thought only sodium comes in. And that's definitely not the case. Even though sodium is the dominant ion, meaning this cell is mostly permeable to sodium, actually calcium is actually leaking in, and a little bit of potassium might be leaking out. So you have other ions moving back and forth as well, even though in this case sodium is the major contributor to the membrane potential. So if that's the case, now let's take another look at the membrane. Now let's take a look at this membrane, and let me show you what might be out here. You've got some receptors on this side, and those receptors are for a neurotransmitter. So there's actually nerves that come down and land right on our pacemaker cell. And these are the sympathetic nerves. Sympathetic nerves. And these nerves are releasing some neurotransmitter. And this neurotransmitter, I'm just going to try to label as I go, is norepinephrine. Norepi sometimes it's called. Norepinephrine. So norepinephrine comes and lands on these receptors and is going to cause a signal into the cell. And it's going to basically tell the cell to be permeable to these ions, allow these ions to flow across the membrane. So they say, okay, fair enough. Now, on the other side, you've got another set of receptors. And of course, it's not actually divided by one side and the other. I'm just doing it just to kind of represent an idea, which is that on this other receptor, you've got other kinds of neurotransmitters landing. And these, right here, are acetylcholine, or acetylcholine. Now, acetylcholine is also going to send a signal down here. And this signal is coming from parasympathetic nerves. Parasympathetic nerves. So you might have heard of sympathetic and parasympathetic nerves. These are both part of the autonomic nerve system. And the parasympathetic nerves are sending kind of an opposite message. They're saying to the cell, well, wait a second, don't allow so much permeability, don't allow so many ions to go back and forth across your membrane. So opposite messages coming in, and as it turns out that they kind of balance and offset each other, and so you get what I've shown you. You get some sodium coming in, a little bit of calcium, and a little bit of potassium leaving. Now, if I was to actually show you now what could happen, let me try to take a little shortcut here and do a little cut paste. Imagine that this happens, something like this. Let's show you. I'm going to have to move this canvas up a little bit. But let's say now you have more sympathetics. Let's say you have more sympathetics coming in than parasympathetics. Then you might get something like this, where instead of just a little bit of neurotransmitter here, let's say you get a lot more. And let's say now this receptor is also firing, and let's say you get a little bit of firing from this receptor. Well, now you get all three receptors on the left, and that really outbalances the one receptor on the right. So your sympathetic drive here, you could say, is much stronger than your parasympathetic drive. And if that's the case, if your sympathetic drive is much stronger, then what's going to happen is you're going to have more sodium coming into the cell. Because again, the sympathetics are trying to get more ion permeability. So you have a lot more sodium kind of gushing in. And you'll get a little bit of extra calcium too. You'll get more calcium here too. And you'll get more potassium leaving the cell. So basically, sympathetics are going to cause all of the ions to increase in the direction of movement. So you're going to get more sodium to come in, you're going to get more calcium to come in, and you're going to get more potassium to leave. So that's interesting, and let's actually just keep that in mind. I'm actually going to do this one more time and show you what could happen if the opposite were true. Let's say that in this case you had more parasympathetic drive. So let's say here you have now, in this third scenario, remember the first scenario is kind of the baseline scenario. In this third scenario, now let's say you have more acetylcholine filling up these receptors, and that's outdoing what the sympathetic nerves are doing. So now you've got a lot more parasympathetic stimulation. Well, now this cell is going to think, okay, well, the parasympathetics don't want as much ion movement, so less sodium. Again, this is all in 1/10 of a second, so if you just catch this cell at 1/10 of a second, less sodium has moved in, maybe less calcium has gotten in, and maybe less potassium has left. So if you look at 1/10 of a second, the pictures, the snapshots are really, really different. So in both scenarios, sympathetics and parasympathetics, it's the same ions. They're moving in the same direction, but what we're looking at is the amount of charge that's flowing over a period of time. And sometimes you might even use the word current. You might say, well, sympathetics are increasing the current, and parasympathetics are decreasing the current, the amount of charge that's moving over a period of time. So how would this actually look on our figure? So we drew a figure at the top. How would this actually look on this figure? Well, I'm going to use the colors red and green because that's kind of what we've gotten into using here. So green, remember, that was our sympathetic scenario. Well, what that's going to do is that's going to basically increase the amount of charge rushing in. And at 1/10 of a second, you've got more positive ions in the cell. So let's say at that point, you've actually already hit threshold, and you might now fire in an action potential, and it will come down just as before. And your heart rate is basically going to go up because you've shortened the heartbeat. And the opposite's going to happen with parasympathetics. So with parasympathetics, you're going to have a longer time to get to that threshold because, again, it's at 1/10 of a second, only a little bit of sodium and calcium were inside and only a little bit of potassium had left. And you're going to have the same, roughly the same looking action potential as before. And you've gotten a much lower heart rate now because the heartbeat is much longer. So you can see that the amount of current that's flowing is changing. And so really we're tweaking phase 4 with our sympathetics and parasympathetics to change our heart rate.